Bismillahirrahmanirrahim. Assalamu alaikum students. Hope you all are fine and doing well at your homes. I'm Mrs. Nadia Rauf from Army Burnhall College for Girls, Ahmedabad. And today we are starting with the second lecture of chapter number 16, that is hydrocarbons. In today's lecture, we are going to discuss physical properties of alkanes. We are going to discuss isomeric alkanes, and we are going to discuss reactivity of alkanes, radical substitution reactions, and in the end we will be discussing about cycloalkanes. By the end of this lecture, you should be able to describe physical properties of alkanes and cycloalkanes. You should be able to name various cycloalkanes, and you would be able to describe radical substitution reactions of alkanes, and you would be able to apply it to methane and ethane as well. Girls, there were some of the questions that were given to you in the previous lecture, and I told you that answers will be given to you in the next lecture. So here are the answers of few of the questions that were given in the previous lecture. First one was the quick quiz, in which 7 questions, short questions were given. Let's see answers of these questions now. The first question was, what is catenation? You know, catenation is self-linkage of atoms of an element to form chain and rings. Among the various elements, carbon is the most common element that has property of catenation. Second question was, what are hydrocarbons? As the name is indicating, the term hydrocarbon stands for compounds of hydrogen and carbon atom only. Question number 3 was, why saturated hydrocarbons are called paraffins? The name is indicating the word param stands for barely or rarely, and affin stands for affinity or attraction. So the word paraffin would mean lacking affinity or lacking reactivity. This word paraffin is very commonly used for alkanes, and it is because of unreactive nature of alkanes they were called as paraffins, because they rarely react with something else. Question number 4 was, why unsaturated hydrocarbons are called olefins? Alkenes are called olefins because they form oily liquids when they react with chlorine gas. Question 5 was, what is hybridization? Hybridization is the concept of mixing atomic orbitals into new hybrid orbitals. The new hybrid orbitals that are made are having different energies and shapes than the component atomic orbital, and they are suitable for pairing up of electrons to form chemical bond. It is in fact intermixing of atomic orbitals to make new orbitals for the incoming electrons. Next question was, why benzene is called aromatic hydrocarbon? The term aroma stands for fragrance, flavor, smell, or odor. Aromatic compounds are those compounds which have got benzene ring in them. Aromatic compounds, this term aromaticity in chemistry is no longer associated with the aroma. In many organic compounds, aromatic compounds, they do not have any smell. But aromatic compounds would be called those compounds that has got benzene-like structure in them. For example, pyridine and indole are various examples. These compounds, they exhibit unusual stability, which is called aromaticity as well. The last question was, what is hexagonal structure? The name is indicating hexa stands for 6, and hexagonal means 6-sided structure. So hexagonal structure, for example, benzene has got a hexagonal structure, you can see it over here, and graphite has got a hexagonal structure in which various sheets of graphite are having hexagonal structure, and these sheets are linked together through van der Waals forces. Another question that was given to you in the previous lecture was, draw the structural or in fact line diagram for each of the following alkanes. These compounds were given to you, and these compounds you had to draw their line diagrams. Now you must have drawn it at your homes. Now check your diagrams and check answers with the ones that I am showing you, whether you have drawn it correctly or not. The first one was 2,3,3 trimethyl pentane. The structure of 2,3,3 trimethyl pentane is this one. Numbering will start from this side, that is 1, 2, 3, 4 and 5. At position 3 there are two attachments, that is CH3 group and CH3 group, and at position number 2 there is also a CH3 group. Next compound was 3-ethyl 2-methyl hexane. The compound is drawn over here. Numbering will start with this side, 1, 2, 3, 4, 5 and 6 carbon atoms. At position number 2 there is a methyl group, and at position number 3 you can see there is a ethyl group. Next compound was 4,4-diethyl 2,2-dimethyl heptane. The structure is drawn over here. Numbering will start from this side, 1, 2, 3, 4, 5, 6 and 7 carbon atoms in all. At position number 2 there are two attachments, that is 2 methyl groups. At position number 4 there are two ethyl groups that are drawn over here, and this is the line diagram for this compound. Moving on to next part, it was 6-butyl 4,6-dipropyl undecane. Undecane stands for 11 carbon atoms. This is the structure of 4,6-dipropyl unbutane. I have numbered various carbon atoms as well. We will start numbering from this side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 atoms, carbon atoms in undecane. At position number 6, you can see there is a butyl group, there is a propyl group present. There are two propyl groups which are present at position number 6 and position number 4. At position number 6, there is a butyl group present as well, which can be shown over here in this way, 1, 2, 3 and 4 carbon atoms. So this is a butyl group, and these two are propyl group. Next compound is 3-ethyl 5-methyl 4-propyl decane. Decane stands for 10 carbon atoms. This is the structure. Again, I have numbered it. We will start numbering from this side. This is carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9 and there are 10 carbon atoms. At position number 3, you can see there is a ethyl group present. At position number 4, there is a propyl group present. There are 3 carbon atoms in propyl group, that is 1, 2 and 3. And at position number 5, there is a methyl group present. There was another activity which was given in the previous lecture from your books. I have shown you the picture in this the previous lecture. I have shown you the activity from your book. Let's find out their answers now. Question number 1 was, name each of the following compounds according to IUPAC system. This was compound number A. The name of the compound is 2,5-dimethylhexane. This is a 2,5-dimethylhexane having 6 carbon atoms in the chain, and at position 2 and 5 there are 2 methyl groups. Check it with you whether you have drawn it, whether you have named it correctly or not. The second one is the structure, and the name of the compound is 2,2,4-trimethylpentane. Now why it is a pentane? We will start numbering from this side. This is 1, 2, 3, 4 and 5. This is the continuous chain. We have to number the continuous chain. In this continuous chain, you can see at position number 2 there are 2 methyl groups, and at position 4 there is another methyl group, so it would be 2,2,4-trimethylpentane. Third structure is this one. Name of the compound is 2,4-dimethylhexane. Again, you have to count the carbon atoms in the continuous chain. Let's start it from this side. That is 1, 2, 3, 4, 5 and 6 carbon atoms in all. And at position number 2 and at position number 4 there are 2 methyl groups, so it would be called 2,4-dimethylhexane. The next structure is this one, D part, and the name of the compound will be 3-methylpentane. Again, count the carbon atoms in the continuous chain. That is 1, 2, 3, 4 and 5, and you can see at position number 3 there is a methyl group present. So the correct name is 3-methyl pentane. The second question of this activity was related to indicate what is wrong with each of the following names and give correct IUPAC names if possible. I am giving you the correct names. The first question was 2-dimethyl pentane. What is wrong with this name? Propane is okay, but dimethyl. So di means there should be 2 methyl groups, but position of only 1 methyl group is being indicated. That is, it is at position number 2. So we need to find out where is present the other methyl group. So the correct name should be either 2-methyl propane with only 1 methyl substituent, or if it is dimethyls, and then it should be 2,2-dimethyl propane. In propane there is no other position except 2 position where 2 methyl groups can be attached. The next compound, the next question was 2,2,3-methyl butane. Again the problem is same as was present in part A. Now 2,2,3 means there should be 3 substituents present, but we have been told only about one substituent, that is methyl. So what are the other ones? Whether it is 3 methyl groups attached or there are some other ones as well, but they have not told us. So the correct name of the compound should be 2,2,3-trimethyl butane. It should be 2,2,3-trimethyl butane. 3 methyl groups should be present. Third part is 3,3-dimethyl 5,5-dimethyl heptane. It's okay with heptane, but there is repetition of one substituent 2 times, which should not be done according to IUPAC. It should be 3,3,5,5-tetramethyl heptane. The name of the compound should be 3,3,5,5-tetramethyl heptane. Next part was 2,2-diethyl 4,4-dimethyl pentane. The correct name of the compound would be 4-ethyl 2,2,4-trimethyl hexane. It is pentane, shown over here that it is pentane, but when we draw the structure, we would see that the longest continuous chain would not have 5 carbons, but instead it would be having 6 carbon atoms in them. If we start numbering from this side, so it will be 1, 2, 3, 4 and 5 and 6 1. There are 6 carbon atoms. At position number 2, there should be 2 methyl groups present and 1 methyl group will be attached over here. In fact, what they have shown you is the pentane. They have told that it's a pentane. So if you take it like this, that is, this is first carbon, second, third, fourth and fifth carbon, and at position 2 there are 2 ethyl groups attached, the name would be incorrect, because at this position this ethyl group will be included in the continuous chain and overall carbon atoms will, the number of carbon atoms will increase in that case. The next structure is 2,4-diethyl pentane. The correct name should be 3,5-dimethyl heptane instead. Again, if we see the structure of this compound and you take this one as the pentane, that is 1, 2, 3, 4 and 5 carbon atom chain, in which at position number 2 and position number 4 there are 2 ethyl groups present, then these ethyl groups would not be acting as a substituent. Instead they would be included in the continuous chain and number of carbon atoms will increase from pentane to heptane. So in fact the name of the compound would be then 3,5-dimethyl heptane. The last part of this question was 3-ethyl 4-methyl pentane. The correct name would be 2-methyl 3-ethyl pentane. It seems that numbering is incorrect in this one. If we draw the structure, we would see that it's a pentane having 1, 2, 3, 4 and 5. If we start numbering from this side, giving the lowest number to the substituents, that is ethyl group and methyl group, methyl will be given position 2 and ethyl will be given position number 3. But what they have done, they have started numbering from this side, that is 1, 2, 3, 4 and 5. So it will be definitely incorrect one. The next part of the same question was draw the structures of the following compounds. There were six compounds that were given to you and you had to draw their structures. I'm drawing their line diagrams in front of you and some of the detailed diagrams as well. The first part was neoheptane. Neoheptane structure is being shown to you over here. This is the neoheptane. As you can see, the continuous chain is not having 7 carbon atoms as it should be heptane, but the term neo is present. The prefix neo is used for those alkanes in which 2 methyl groups are attached to the second last carbon of the continuous chain. This is second last carbon of the continuous chain, and you can see at this second last carbon atom there should be 2 methyl groups. So these 2 methyl groups are attached to the second last one, so that's why 2 carbons would become less in the continuous chain. Overall there should be 7 carbon atoms, right? The next structure is isoheptane. The structure of isoheptane is being shown to you over here. Do remember the prefix iso is used for those alkanes in which 1 methyl group is attached to the second last carbon atom of the continuous chain. If we talk about the second last carbon atom of the continuous chain, it will be this one. Like, let's start numbering from this side. 1, 2, 3, 4, 5 and 6. In the continuous chain there are 6 carbon atoms only, and at second last carbon atom you can see it is attached with 2 more carbons. One is this one and one is this one. So this structure would be called isoheptane, right? The next structure is trimethyl ethyl methane. You have to draw first of all a methane carbon atom which should be linked with 4 more things. And what are those 4 more things? Out of which 3 of them are methyl groups that are attached over here, and one of them is the ethyl group. The next question is dimethyl ethyl isopropyl methane. Again, you have to draw a methane which should be having 4 bonds, and out of these 4 bonds 2 should be the methyl groups, one of them should be the ethyl group, and one of the group attached would be the isopropyl group. You can see this is the isopropyl group in which central carbon is attached with the major chain. Next compound is dimethyl propyl ethyl methane. Again, draw a methane, draw 4 bonds with the methane. In these 4 bonds, out of these 4 bonds, 2 of them should be the methyl groups. One of them should be symbol propyl. When there is nothing written, it means it is N-propyl or normal propyl chain. And this is the normal propyl chain attached with the terminal end with the major chain. And this is the ethyl group being attached over here. These are not IUPAC names which are given to these structures, okay? These are just common names. The last part is 3-ethyl hexane. This is a hexane having 6 carbon atoms, and at position 3 there is a ethyl group attached. Okay, that is all from the previous lecture. Some questions from the previous lecture. Here are some questions for you to practice at your homes. Some more examples are being given to you. Give IUPAC names to the following structures. These are various structures. There are various parts. Now these are the normal structures. Bonds are not shown, but it's okay. We can simply write CH2 in the middle and CH3 at the terminal end. If branching is present, then one of the hydrogen would reduce. You have to give them IUPAC names, keeping in your mind all of the rules that you have studied in the previous lecture. Okay. Now we are starting with the physical properties of alkanes. Physical properties means the properties which are related to the physical phenomena, like physical state of alkanes and melting boiling points and the intermolecular attractive forces that are present in them, etc. Physical properties, the first important property is the physical states of alkanes. Do remember, girls, these alkanes are usually from carbon number 1, that is methane, to carbon number 4. These are usually gases at room temperature. As the chain length increases from carbon number 5 to carbon number 17, These alkanes are liquid at room temperature. For example, kerosene, you might have seen kerosene lamps, kerosene oil which is burning in them. This is a liquid. And from carbon 18 onwards, these are all solids, which are usually the butamin, which is usually used in the road surfacing and waxes, etc. These are all solid state substances which are having carbon atoms more than 18 in them. Some other physical properties of alkenes are, these are usually non-polar in nature or very weakly polar. That means they won't dissolve well in water. In fact, they would be soluble in the non-polar solvents like benzene, carbon disulfide, etc. They have very low melting and boiling points because, as physical states are indicating, their melting and boiling points are overall very low because they are usually either liquids or gases or soft solids. Their melting and boiling point usually increases with the molecular mass. Molecular mass means as the chain length is increasing, you have seen that their physical states are changing from gaseous to solid state. So that's why their melting and boiling point would definitely increase with that. And boiling point usually decreases with the increased branching as well. If there is a straight chain molecule and you are comparing it with the branched chain molecule having same number of carbon atom, you would see that branched compound will have lesser boiling point as compared to the straight chain. Why it is so? You might have heard that it is easier to pick up peas from the noodles. Consider noodles are the long chain carbon atoms and they can get intermingled with each other more, and they would be more messy. Instead, you can easily pick up the peas, that is the branch structures, which become more compact. So they can be separated very easily. So that's why the boiling point of branched compounds are usually less as compared to the boiling point of long chain compounds. And it is usually seen that example of normal butane and isobutane can be given at them, although both of them have got same number of carbon atoms. They have got high vapor pressure as well. Vapor pressure means they can be evaporated very easily and they would make a lot of vapors because of course they are non-polar, they have low melting and boiling point, so that's why they will exert too much of vapor pressure or they would be vaporized very easily. Girls, make a correction in your books. It is written that N-butane has a boiling point of 55, but it is not 55 degrees centigrade. It is instead minus 0.4, or in some cases it is written as minus 1 degree centigrade. So it is a higher boiling point as compared to isobutane, which has got minus 10.2, and sometimes in some texts it is written as minus 11.7 as well. Okay, the next topic is isomeric alkanes. You are familiar with the term isomer. Iso stands for same and mers means parts. Isomeric alkanes are those alkanes which are having same molecular formula but their structures are different. Isomerism can be of various types that will be discussed in detail in this chapter later on. But the isomerism that we are discussing over here is called structural isomerism of alkanes. Alkanes usually with more than 3 carbon atoms can show structural isomerism, that is from butane onwards various isomers can be considered. Isomers of butane, there are 2 isomers of butane, that is normal butane and methyl propane. These are the structures that are being shown to you. N-butane has got formula of C4H10 and methyl propane has also got formula of C4H10, but the branching is different. One of the methyl group in the butane chain is being detached from here and it is being attached at the middle, making it a isobutane or methyl propane as well. Their properties, isomers are those compounds which are having different physical properties and chemical properties as well. The physical properties which are different can be seen over here. The boiling point of N-butane is 0.4 degree, minus 0.4, and isobutane is minus 10.2. Similarly, their melting points you can see are also different from each other. Some isomers of pentane are being shown to you as well. As the number of carbon atoms would increase, the number of isomers would also increase. Pentane has got 5 carbons in all, and it has got 3 isomers, that is pentane. It is 2-methyl butane, which is also having overall of 5 carbons and 12 hydrogen. So it is also an isomer of pentane, and we can have 2,2-dimethyl propane as well, in which you would see there are again 5 carbon atoms and 12 hydrogen atoms in them. This 2-methyl butane can be also called isobutane, and this structure can be called isopentane, and this structure can also be called neopentane. I've already told you about the term iso and neo. What are these? Moving on towards next topic, which is related to the relative stability of alkanes. Longer chain alkanes are usually more stable as compared to the shorter chain alkanes. Again, the stability means longer chain alkanes, they can develop stronger intermolecular attractive forces among each other as compared to short chain alkanes. You might be familiar with the London dispersion forces. You have studied it in detail in class first year as well, that long chain compounds can be bonded together through a strong intermolecular attractive forces, and usually more branched compounds are more stable as compared to the straight chain alkanes. For example, we can have example of 2-methyl propane, which is more stable than butane. 2-methyl propane is in fact isobutane as well. When we talk about the term stability, we have compared these two compounds previously in the previous slides as well, and these two compounds were compared on the basis of their boiling point. Right now we are not discussing boiling point, we are discussing their stability. What is meant by this term stability? In everyday language, usually a chemical substance is said to be stable if it is not particularly reactive in the environment or during normal use, and if it retains its useful properties on the time scale of its expected usefulness. That compound would be called a stable compound. In particular, the usefulness is retained in the presence of air, moisture, heat, or under expected conditions of applications. In this way, we can say that a compound is said to be unstable if it can corrode, decompose, polymerize, burn, or explode under the conditions of anticipated use or normal environmental conditions. We know that these branch chain alkanes usually are having lesser surface area available for the reaction as compared to straight chain alkane. So that's why I told you that they are in the form of peas, or they are rounded structures, so they have lesser surface area available. They are straight chains, so they are susceptible for reactions more. They are, you can say, they are more open for the reactions as compared to the branch chain alkanes, which are less open for the reactions. So these were some important physical properties that we have discussed for alkanes. Moving on towards chemical reactions of alkanes or chemical reactivity of alkanes. Alkanes are usually not very much reactive. When we talk about the term reactivity, that in fact means unreactivity of alkane. As it is best depicted in this picture, I can, but I won't. They can react, but they won't react with anything else. The reasons for unreactivity of alkanes can be, first one is the non-polar bonds. All of the alkanes, we know that they have got only carbon and hydrogen atoms in them. Carbon has got electronegativity of 2.5 and hydrogen has got 2.1. So the bond is totally non-polar. There is no electronegativity difference between them. You know, non-polar bonds are usually very less reactive as compared to the polar bonds. So that's why they are unreactive in that case. The next reason, or the second reason for that, is inertness of a sigma bond. Sigma bond is usually inert. Inertness again means unreactivity. Sigma bonds are usually formed by, end-to-end overlap of orbitals. So the electrons are on a line joining the two nuclei. They are so strongly attracted to the nuclei that other reactants have got difficulty in removing them. So that's why sigma bonds are not very reactive ones. Having said that these are very unreactive compounds due to these two reasons, so these reactions of alkanes are usually not possible. The only reaction which is being discussed in your books is the radical substitution reactions of alkanes. They are available. What is radical substitution reaction? It is in fact substitution. Substitution means removal of one of the hydrogen from the alkane and substitution of halogen in the place of hydrogen to make alkyl halide. This would be called a substitution reaction. Hydrogen has been substituted by a halogen group. Alkanes, they undergo substitution reaction, and the reactivity order for them is, this is 3 degree means it is tertiary alkane. They are very much reactive towards substitution. Then comes secondary alkanes. This 2 degree stands for secondary alkanes, and this 1 degree stands for primary alkanes. So tertiary alkanes will be much more reactive towards substitution as compared to secondary, and then comes primary alkanes, for example methyl or methane, we would say. Halogen's reactivity towards substitution is fluorine would be very much reactive. It is that much reactive that it usually explodes. The reaction usually explodes when fluorine is reacting. Chlorine reacts at a good rate, and bromine is also showing a good reaction. Iodine is too slow, so reactivity in that case for chlorine and bromine is quite good, but for fluorine and iodine it is not noticeable. So we are going to discuss only chlorination and bromination in the case of substitution reactions. To remember, girls, this reaction proceeds through a radical chain mechanism. We are going to discuss this mechanism in detail, what is meant by radical chain. There are two possibilities for the reaction to occur. First possibility is we can have the reaction at room temperature. When methane and chlorine are mixed together at room temperature in the absence of any sunlight or any other source of energy, nothing would happen. You would keep the mixture for a longer period of time. Even then, both of them would not react and they would have no reaction with each other. But if you are providing the same reaction with some sunlight or any other form of energy, high temperatures are provided, then in that case the process would start. Methane would start reacting with chlorine in the presence of sunlight, and they would make a haloalkane, that is alkyl halide. In this case, alkyl chloride or methyl chloride is being produced. Along with that, HCl is being produced. This was the general reaction. Now the detailed mechanism is being shown over here. This radical chain mechanism is in fact a 3-step process. The first step is initiation, the second step is propagation, and third step is termination. Let's discuss all these 3 steps in detail now. First of all, initiation. Initiation breaks the bond between the chlorine molecules, and it usually happens due to the energy, that is sunlight or heat is usually provided. For this step to occur, energy must be put in. This step is not energetically favorable without the input of energy. After this step, the reaction can occur continuously as long as the reactants are provided without input of any more energy. But for the starting up of this reaction, some energy is required to break the bond. Do note that this part of mechanism cannot occur without any input of energy. So any form of energy, that is light or heat, it can be sunlight, it can be any other form of light or heat, can be provided to start the reaction. This is the first step, initiation step of the reaction. In this step, the bond between the chlorine molecules, there are 2 electrons that are shared between chlorine atoms making this bond. They will be broken up homolytically. Homolytic cleavage means both of the chlorine will take one electron from the bonded pair, and there will be a homolytic cleavage between the chlorine atoms to make two chlorine radicals. These are not chlorine atoms anymore. They have been separated from a molecule. They will have their own set of electrons, but they would be very reactive. They would like to react with something else immediately. So that's why these are called radical. This is the difference between atom and a radical. Both of them have got same set of electrons, but radical is the one that is produced within the reaction mixture from a compound, and it is in a very reactive state to combine with something else. The next step of this reaction is propagation step. Propagation step is again a two-step process further. In this step, in the first step, chlorine radicals that are produced in the first step of initiation, they will take up hydrogen of the methane and they will make HCl and methyl radical. This is happening in this way. This electron, which is very reactive, is combining, or it is breaking this hydrogen and it is combining with this hydrogen. Again, there is a homolytic cleavage between hydrogen and this carbon atom as well. Both of them are taking one electron of the bond breakage. Hydrogen will combine with chlorine, making HCl, and a new radical which is called methyl radical would be produced. Again, this carbon has got an electron. It is its own electron, but it has been separated from the molecule and it is in a very reactive state right now. So it would again be called a radical. The second step of this one is the chlorines which were present as a reactant. They will again be utilized, and one of the chlorine atom would become a radical and other one would combine with the methyl radical. The chlorine atoms which are present in the reactant, again they will take part in this step. They are taking part in two steps. First one is their action in the initiation step, and second one is their action over here in the propagation step. Now they are again combining with a methyl radical. So methyl radical is bringing its own electron. They will again undergo homolytic cleavage. One of the chlorine will combine with the methyl radical and it will make the resultant product, that is methyl chloride. And one of the chlorine will be separated out again in the form of radical. Now you can see another radical has been produced which is in a very reactive state. So this reaction will now continue on. Initiation step required some energy, but later on no energy is required. The radicals will be produced on their own and they will keep on reacting in the reaction mixture, and they will keep on carry on the reaction. That's why it is called a chain mechanism. This is a chain reaction. The last step of this reaction is termination step. Termination step will end up in terminating or ending up the reaction. All of the remaining radicals which were produced in the course of the reaction, they will combine together to make up compounds and they will stop the reaction. They can combine in three possible ways. They can make more of the products, that is CH3 and Cl can be produced in this way. There are many methyl radicals being produced. There are many chloride radicals being produced, so they can combine together to make up more and more of the product. They can be more reactants can be produced, like two chlorine radicals can combine together and they can make chlorine molecules. So reactants will be produced and they will stop reacting now. And the third important case is when there can be many, because there are many chloride radicals and there are many methyl radicals. So some methyl radicals will combine with each other as well and they will make a long chain molecule, that is ethane molecule. This is how these two methyl radicals are combining together to make up a ethane molecule. And this is how this process would end over here. But there are some problems which are related to chlorination of methane. Usually the chlorination of methane does not stop after one chlorination. Once the product is produced, you are unable to stop the reaction, and the chloride radicals, if they are present, even if a slight amount is present in the reaction mixture, they would carry on combining with the methyl chlorides, and they will continue on, and they will keep on taking all of the hydrogens from the methyl chloride, and they will keep on making di and tri and tetra substituted products. So mono-substituted chloromethane, it will be very hard to get it in the separated form. In fact, di, tri and tetrachloromethanes can be produced in the reaction. How can we control this overchlorination of methane? One way to avoid this problem is to use much higher concentration of methane in comparison to chloride. This reduces the chance of a chlorine radical running into a chloromethane and starting the mechanism over again to form a dichloromethane. Through this method of controlling product ratios, one is able to have a relative amount of control over the product. Because of these problems that we face during chlorination of methane, it is usually not very much preferred, I would say. The next bromination of methane is being given in your books, but again it will be following 3 steps, that is initiation, propagation and termination. But in your books, sequence is a little bit disturbed. I'm showing you the correct sequence. You can please mark it in your books. The first step is initiation, where bromine radicals will undergo homolytic cleavage to make bromine radicals. Bromine molecule is breaking up to make bromine radicals. Second step is propagation, which is 2-step process in which bromine radical will take up one of the hydrogen from the methyl methane and it will turn it into a methyl radical. Along with that, HBr is being produced. And when the second step is bromine will again, reactant bromine will combine with more of the methyl radicals to make up the product, that is bromomethane, and bromine radical is produced which can be reused again. So propagation step will continue on and on and on to make the chain product. The last step is termination step. As I told you, there can be 3 possible ways for terminating this reaction. Methyl radicals can combine together to make up ethane. Bromide radicals can combine together to make up bromine molecule, and bromide radical and methyl radical can combine together to make up bromomethane as well. So this is how reaction would stop. In your books, a little bit sequence has been disturbed, so you can please mark those steps as initiation, propagation and termination in your books. Now moving on towards next topic, that is cycloalkanes. Cycloalkanes are those compounds which are present in the form of cycle. Here we are going to discuss only cycloalkanes. Cycloalkenes and cycloalkynes would not be discussed over here. Cycloalkanes, I have told you already, these are hydrocarbons. They have in which carbon atoms are arranged in the form of rings. These are all saturated compounds. We are discussing only cycloalkanes, not alkenes or alkynes. Their general formula is CnH2n. They are 2 hydrogens less than the normal alkene, because the terminal carbon atoms, they lose 2 hydrogens and they link up with each other to make a ring-like structure. The smallest cycloalkane is cyclopropane. We do not have cyclomethane or cycloethane in that case. Some examples are being shown to you. This is the structure of cyclopropane. You can see there are 3 carbon atoms which are arranged in the form of a triangle. We can have cyclobutane, where 4 carbon atoms, all of the carbon atoms are sp3 hybridized and all of them are having 2 hydrogens with them. This is cyclopentane. 5 carbon atoms are present in this structure and they are in the form of a pentagon. Cyclohexane is shown over here in this structure, where 6 carbon atoms are arranged in the form of a hexagon. Various cycloalkanes, their molecular formulas are being shown and their basic structures are being shown as well. This is a cyclopropane, C3H6. You can see there are formula is having 2 hydrogen less than the normal alkane. We can have cyclobutane, we can have cyclopentane, we can have cyclohexane, we can have cyclopenheptane, cyclooctane in the form of an octagon, cyclononane, and this is the representation of a cyclodecane. This is how 10 carbon atoms can be arranged in the form of a ring. Physical and chemical properties of cycloalkanes are almost similar to that of alkanes. They also have low polarity of bonds. Their intermolecular forces, London dispersion forces, are very weak. Their melting and boiling points are also less, and they are also very less reactive as like alkanes. Let's discuss some rules of IUPAC rules for the nomenclature of alkanes. The first rule is the same as we have discussed for alkanes. We have to determine the parent chain in the case of alkanes, and right now we are going to determine the parent ring. If there are 2 cycloalkanes, then we are going to use the ring that is having more carbon atoms in them. Choice between alkyl straight chains and cycloalkanes cannot. If there is a alkyl straight chain that has a greater number of carbon atoms than the cycloalkane, then alkyl chain must be used as a primary parent chain, as it can be shown over here in this compound. There is a propyl group which is acting as a substituent, and this is the parent chain or parent ring. It is having 6 carbon atoms in them. So this will be taken as a parent chain, and this will be taken as a substituent because it has got less carbon atoms as compared to this one. So it would be called propyl cyclohexane. But in this compound, you can see the parent chain is having 4 carbon atoms and the substituent is having less carbon atom. The cyclo group is having 3 carbons only. So cyclo group would now be taken as a substituent and parent chain will be the long chain. So the name of compound will be 1-cyclopropylbutane. When it is acting as a substituent, as I have told you in the previous example, the cycloalkane would become cycloalkyl. A and E would be replaced by the term -yl. So it would be named as cycloalkyl group if it is acting as a substituent. For example, cyclopropane would become cyclopropyl, cyclobutane would become cyclobutyl, and it would become cyclopentane would be called cyclopentyl, and cyclohexane would be called cyclohexyl if they are being utilized as a substituent. After determining the parent chain, we have to see the substituents which are present on the parent ring right now. We will have to number the substituent in such a way that carbon which has got a functional group or attachment upon it should have the lowest possible number. For example, the compound shown over here to you people is cyclopentane. There are 2 substituents. How you have to number it? We have to start numbering from any of the substituent can be given number 1 right now. But how you move on in the ring, this is very important. If you start numbering from this carbon atom, this can be number 1, this can be 2, 3, 4 and 5. This is the correct numbering. So the correct name of the compound will be 1,2-dimethyl cyclopentane. This will be position 1 and this is 2. You can call this carbon as position 1 and this one as 2 as well. But do not start in this way so that this carbon gets position number 1 and this one gets 2, 3, 4 and 5. This will be wrong. The second rule is if there are multiple substituents that are present on any of the carbon atom, then the carbon atom which is having more substituents will be given the lowest number. For example, again in the same case, if I attach one more methyl group with this compound, now which carbon will be given number 1, this one or this one? Now the carbon atom having more substituents, this carbon is having 2 substituents and this carbon is having 1 substituent only. So we are going to give number 1 to this carbon atom, right? So number 1 carbon is having 2 methyl groups and this is carbon 2, this is carbon 3. 3 methyl groups are attached at position 1, 1 and 3. It would be called 113 trimethyl cyclopentane. If there are multiple substituents that are present, then we are going to use the rule of sum of substituents for the multiple substituents, as we have done already in case of alkanes as well. You can see in this example there are multiple substituents which are present at position number 1 and 3 as well. And how you are going to number it, we can start numbering from this side, that is 1, 2, 3, 4, 5 and 6, so that substituents are getting number 1, 1 and 3. If we start numbering in otherwise way, that is from this side, in that case the overall numbering will be, this is carbon 1, 2, 3, 4, 5 and 6 carbon atom, so the numbering will be 133, because there are three at position number 3 there are 2 methyl groups present. So overall sum in this case will be 5, but overall sum in this case will be 7. So this numbering hexane, this numbering will be followed. This is the correct name of the compound, which is at position number 3 there is ethyl group, at position number 1 there are 2 methyl groups present. We have to place substituents and functional groups in the alphabetical order as well. If there are multiple functional groups and we are unable to decide which one should be given the lower number, we have to see their alphabetical order. In this example, if we start numbering either from this side or from that side, in both of the cases, bromine comes first of all in the alphabetical order, and when comparing chlorine, bromine and methyl, but bromine can never get number 1 in that case. It will always get number 2 from this side and from this side as well. But we have to follow the numbering scheme in which most of the substituents should be getting the lower number, which are alphabetically following the lower numbers. For example, in this numbering scheme, chlorine will be given number 1, bromine will be given number 2 and methyl will be given number 3. So the name of the compound will be 2-bromo 1-chloro 3-methyl cyclopentane. Girls, do remember the bromo will always be named first, then chloro, and methyl will be named later on. We are following the alphabetical order in this case. If unsaturation is present, then multiple bonds, double or triple bonds, they will be given the lowest possible number, no matter where is the functional group present or where is the substituent present. This compound, if there is a double bond present, it would be called cyclopentene. This compound is a cyclohexane, but there are 2 double bonds present, so it would be called cyclo-1,4-hexadiene. Diene stands for 2 double bonds, and they are at position number 1 and 4, so you always have to start numbering from the side where double bond is given the lowest number. And do remember, both of the carbon atoms that are holding a double bond should be given the lower number. Means it should be 1, 2, 3, 4, 5 and 6. It should not be 1, 2, 3, 4, 5 and 6. These two carbon, both of the carbons should be getting the lowest number. Similarly, it can be called as cycloben-3-pentadiene 1, 2, 3, 4, 5 and 6. Here are some questions for you to do at your homes regarding nomenclature of cycloalkanes. Give IUPAC name to the following cycloalkanes. Practice all these at your homes and you will be given the answers of all these questions in the next lecture, inshallah. Okay girls, have a good day. Thank you very much. Allah Hafiz.